Welcome to this video on discrete diffusions. Now, you might already be familiar with diffusions on continuous data, as whenever you, for example, generate images here of Paris in the 1960s, the model starts with random noise and then gradually denoises this into the actual image that you wanted to generate. And more recently, there have also been attempts at making this kind of denoising approach work on discrete data, such as language. And here I'm showing you an example from a company known as Inception that shows that their approach of discrete diffusions can actually beat, in terms of speed and potentially also performance, the regular baseline of autoregressive modeling. Now, before I'll show you how these discrete diffusions work, a quick recap on autoregressive modeling. So in autoregressive modeling, everything is based on this idea of predicting the next token conditioned on the past. So the probability of a sequence is decomposed into these conditional probabilities of how likely is the current token conditioned on everything that came before it. And also the training loss that we use is essentially the log probability that the model assigns to the true next token, conditioned on or when feeding the past sequence into the model. A quick image of how this works. We basically start during training with our ground truth sequence x1 up to x4, and then we teach the model to predict the next token x2 conditioned on x1, x3 conditioned on x1 and x2, and so forth. And during inference, we then predict the next token, we append this token into our sequence, we predict the next one x6, and we continue in this way. So everything is based on taking a sequence and conditional on this current sequence predict what would come next. And if we look at the leaderboards of current language models, most of the models that will be at the top are indeed going to be these kind of autoregressive models. But what is interesting is that, again, more recently, models such as Mercury, which is this discrete diffusion, have on certain evaluations, so in this case on output speed, began to beat these autoregressive approaches. And here again, you kind of see that they really showcase that their model gets much faster to the output than the autoregressive one, which is limited by this next token prediction. So why might we be interested in looking beyond these autoregressive models? Well, I think the general answer is that it's always good to think about new architectures and how we could be improving the things that we're currently doing. But to make this a little bit more specific, there are potentially some fundamental limits to modeling things in an autoregressive next token prediction way. There is this paper known as the reversal curse that basically shows if a model is trained on A is B, it doesn't necessarily learn that B is then also A. So from the paper, they write that if we teach the model that Valentina was the first woman to travel to space, it doesn't mean that this autoregressive model will automatically be able to answer who was the first woman to travel to space. So maybe there are these fundamental limits to the approaches that we're currently most focused on. Another one that is related is this lack of self-correction. So in 2024, which is already a long time ago in AI space, there was this paper, large language models cannot reliably self-correct yet. And what they basically did is they prompted a model to answer a question, and then they said, okay, assume that the answer that you yourself gave could either be correct or incorrect, review it and report any problems that you can find. And what they saw is that after having the model self-correct itself, the performance on all benchmarks actually drops. So maybe there is something in this autoregressive token by token approach that whenever you start to make a mistake, these errors will kind of compound and you will never be able to steer yourself back to a trajectory that makes sense. And the final one, which was the one that is highlighted by Inception, is really speed. In the last years, there has been a lot of effort to make these autoregressive transformers really efficient. All kinds of different approaches like the KV cache, where we save keys and values from the past sequence, flash attention, which reorganizes attention computation, and all kinds of attention innovations like multi-query or grouped query attention. Fundamentally, with autoregressive modeling, we're always limited by this idea that we can only generate token T if we've generated all the tokens that came before, so T-1, T-2, and so forth. So we really are limited by this idea of predicting the next token one by one. And then what is the idea with diffusions? So as I already said, following this analogy of images where we start with random pixels, we want to do the same here, but starting with kind of random token slots or masked tokens, and then gradually denoise this into an actual sequence of tokens that will hopefully make sense for whatever task we're trying to solve. In this case, we see that Inception begins with completely random tokens, Zap, Mango, Crisp, Lunar, And then during the generation process, they denoise these guys into tokens that amount to the quick brown fox jumps over the lazy dog. So a sort of coherent sentence. So what are the promised benefits that these diffusion models could give us? I already mentioned speed, but I should be more precise here as to why would we be able to be faster. It is this idea that we are not limited by one generation, but we can actually denoise multiple tokens at once. The second thing is that very maybe there is actually some accuracy we can gain. As I said, this kind of fixed order generation, this autoregressive one-by-one approach, it might have fundamental limits such as errors, which might get amplified, or we cannot solve this ABBA reversal task. And the third thing, which I heard in an interview with Stefano Ermon, who is one of the founders of Inception, is that also these diffusion models, they might just give us more axes of control, so more things that we could play around with in order to get to better results. So we can have different noising schemes, we can have different denoising orderings, and maybe this would lead to, this flexibility would lead to better performance. Okay, if after this video you think, let me learn more about this, then these are the papers that I would recommend, and these are also the ones that I've used to make this video. I think large language diffusion models for me is the one that I found the easiest to read. Structured denoising diffusion models in discrete state spaces is also a more classic approach that introduces the same ideas. And then two more recent applications, scaling diffusions from autoregressive models and block diffusions, also have a lot of interesting elements in them. Okay, so if we want to introduce diffusion models, there are a few different steps that we should discuss. There is the forward process, so how do we go from a coherent sequence of tokens to actually our noised sequence of tokens. Then we need to discuss the model that we use and the loss function that we use to optimize the model. And then we also need to talk about the backward process. And I think a lot of these things can be understood really very intuitively. But if you read many of the papers, they also include a lot of maths. So I'll sort of try to combine the two things. I'll try to present the intuitions and the actual things that we do, but I'll also show you a bunch of different maths just so you know like the full story, and so these other papers also make sense. Okay, so let's begin with the forward process, which is this idea of we are starting with a sequence x0, which consists of tokens x1 up to x capital L. And then we want to have a forward process that would sort of taking us from time t is 0 to t is 1, gradually mask or corrupt or noise these tokens. And in this case, I'm choosing masking as my corruption process, which means that to go from my sequence at time t minus 1 to my sequence at time t, I basically say, I stay at the token that I'm currently at. So I keep token xt I equal to xt minus 1i with a particular probability 1 minus beta t. Or I actually choose to mask this token, so to corrupt it with this probability beta t. And once I have masked the token, in every consecutive time step, it will always remain masked. So this forward process is really about starting with a coherent set of tokens and then masking randomly certain tokens as we move from t is 0 to t is 1. Now, how specifically we add this noise? You can frankly choose this noise schedule as you wish. You could say you start with very little noise, you can linearly increase this noise, or in other kinds of different ways. This is really a design choice of how you actually choose to noise your sequence. In many papers, they are also a little bit more formal whenever they define this forward process, and the way that they typically write it down, which is a nice way to write it down, is by working with this categorical distribution, which models the probability over the vocabulary of tokens that we have. So looking again at one specific token, xti, which is the one-hot encoding of the token that we're interested in modeling. This is basically modeled as this categorical distribution over this Q, which is a matrix of probability, which is the probability of transitioning from state I to J, applies to our token that we had in the previous time step. So this Q, which is this matrix that will define with which probability are we sampling from our vocabulary whenever we want to get to the new state of the token I. We can choose it in many different ways. We can randomly shuffle the tokens, we can mask it with arbitrary tokens, or we can mask it with the mask token, which is the approach that I am describing here. And this approach is also known as this absorbing state diffusion. And in that case, this Q takes on this following form as this 1 minus beta t identity matrix plus beta t times this vector of all ones multiplied by our mask token, our one-hot encoding of the mask token. So really all of this it literally is just saying with this probability 1 minus beta t, we're staying at the token we're at, and with probability beta t, we become masked. But if we want to write this down nicer with this categorical distribution, then this is the way we define Q. You can then write out Q as this k by k matrix, where k is our vocabulary size. And to be very specific, suppose that you at time t minus 1, your ith token is given by 0, 1, 0, 0. This is your one-hot encoding. Then basically our xti is sampled from a probability vector which is given by q applied to xt minus 1i, which basically amounts to, as I said, with probability 1 minus beta t, we stay where we are, so we remain the exact same token that we had. Or with probability beta t, we actually mask ourselves, so then we shift to being the one-hot encoding of the masked token. Okay, we can then also write down the direct distribution for xt conditional on our initial correct uncorrupted sequence, which is literally just written down as this summation with alpha t now being the probability over these 1 minus beta t, so just this compounded probability, which basically says that if a token was never masked, we have xt being equal to whatever the token was at time 0 with this probability alpha t, and if it was masked at any intermediate time between 0 and the t we're currently looking at, then it will have the masked state, and this happens with this probability 1 minus alpha t. Okay, a very, very, very long description to basically just say that we are starting with a sequence, masking it up to get the values at the particular time t. We are randomly masking some of the tokens, and then this sequence is the thing that we will pass into our model. And the model that we can have can literally be any of your favorite architectures, such as a transformer, and everything is exactly the same as in language modeling, in the sense that this sequence where part of our tokens are now masked gets passed into this transformer. And in the output layers, we have these probability distributions which say, okay, this is the probability that this token should be representing this. And specifically of interest are obviously the tokens that were masked in our initial sequence, as these probabilities will represent what these unmasked tokens could actually be looking like. And the crucial thing to mention here is that since we are moving away from this autoregressive one token by one token generation approach, we no longer necessarily have to use attention that is causal. We can actually let our attention be non-causal, because we want the mask token at position 3, for example, to also already know what comes after it, instead of only being restricted to knowing what came before. Okay, and then as for the loss function that we will use, intuitively, again, very, very obvious that this should be the choice. We would basically look at the regular loss that we had in autoregressive modeling, where we look at the probability that the model assigns to the correct token, when starting with our sequence of tokens that came from the forward process, so this noised sequence of tokens. And we're only really interested in computing the loss at the locations where this xt was actually equal to the masked token. So we are only teaching the model to basically get good at demasking the tokens that were masked in the sequence that we passed it. And if you're familiar with this BERT demasking objective, essentially this is very, very close to this, except that in this case, in every iteration, we will choose like a different t, which will amount to a different set of tokens that we are masked. So we really are teaching the model to be working with an arbitrary masking arrangement. Okay. If you, again, want to have more maths, if not, you can also skip these slides. But we can also derive the loss in this kind of more fundamental way by working with the backward process and this evidence lower bound, ELBO. And now to save myself time with typing formulas into Keynote, I will for now just drop the dependence on a specific token, but remember that everything that I write down here is really about the probabilities of this particular token changing its state to something. So remember that we had already derived the probability that a token at time t is given by this alpha t, which was this probability of our individual stay the same or get masked probabilities, plus this 1 minus alpha t times the masked token. And more generally, so generalizing this to any time s that came before t, it would look like this formula with the same logic, the probability with probability alpha t over alpha s, the token kind of survives unmasked from s to t, and with the remaining probability 1 minus that thing, it would actually get masked somewhere in this interval from s to t. So once we have that, we can then actually derive the backward process, which is the probability of xs at the time s that came before t when conditioning on xt. That guy itself is actually, we cannot get it in closed form, so we additionally assume that we condition on x0, and then we can derive this expression which I'm showing you here, which essentially means that if we know that x at time t is already masked, that means that it either was masked before s, and in this case xs is also masked, or it was masked after s, and then xs is equal to x0, and this x0 we can then derive with these conditional probabilities in the same logic that we derived the things before. Okay, so why did we go through all of this hassle? We would like to choose a sensible parameterization of the probability distribution of xs conditioned on xt, and we basically decided to then take it into this form. So we parameterize this p theta that we want to optimize in the same shape that we had just derived for this q of xs conditional on xt and x0. And the thing that gets replaced is that we are no longer working with x0 because we don't know it. We are instead working with this model output whenever we pass in xt. Okay, we're almost at the loss. To get to the loss, we would then basically use this evidence lower bound, which I won't go into detail here, but it's this very standard upper bound on the negative log likelihood of our sequence, which basically gets decomposed into these KL distances. And the term specifically of interest is this last term that we have here on the right-hand side, for which we can actually derive, if we use this parameterization that we just chose for p, and we use the q that we had also derived, we can essentially derive that this KL distance between the q and the p is equal to this guy that we have here, which literally says that we are using our ground truth token x0, the one-hot encoding of it, multiplying it with the log of what comes from the model when passing in our noise sequence. We only care about this whenever xt is actually masked, so we're only considering this loss in the masked locations. Why is this the case? Because this KL divergence drops out for anything that is not x0 that is not x0 when xt is not masked. And we have this probability, this fraction in front of it, which came from this part of our p and of our q. So all in all, this last term of this evidence lower bound is given by this summation. We typically drop this summation because we approximate it by sampling just over a single time step. End of all my maths. Essentially, the loss that we then derived through this backwards evidence lower bound approach is exactly the loss that I had already shown you. We only care about the probability that the model assigns to the ground truth tokens in the masked locations. So whenever we take in a sequence masked 2 times t, we care about the outputs that the model gives us, the probabilities at the masked locations, and we have this standard loss function. And the only difference between what I had on this page and what I'm showing you now is that whenever I choose the noise schedule to be equal to just be given by beta t is t, I just end up with this 1 over t here instead of this alpha thing that I had before. Very closely related to the autoregressive approach, except that we are now sampling over t, so we are feeding in arbitrary maskings of our ground truth sequence, and we only care about the loss in the masked token locations as opposed to caring about them in all locations. And the crucial distinction, we are moving away from conditioning only on what came before it, and instead we condition on the full sequence xt. And if you want to see more on how this is derived, I like the derivation that they had in scaling diffusion language models via adaptation from autoregressive models. Okay, a lot of maths, but the idea really is extremely simple. So whenever we train the model, we take our sequence, so we sample our sequence from our big data set that we're using, we sample a particular time t, which will tell us how much are we actually noising this particular sequence in this iteration. We then noise, aka mask the tokens with this forward process that I had defined, which basically says every token remains as is with a given probability, or it gets masked with this other probability. This gets passed into our language model. Then we get the probabilities that the model assigns to the previously masked tokens. And then we do the same thing again with a new sequence. So we take the new sequence, sample at t, noise the tokens, and again get these probabilities, pass them through the loss function, updates parameters, and then we do it again, take a sequence, noise, pass through the model, get probabilities, and updates parameters through the loss function. To be concrete, this is the algorithm that Lada, this paper on language diffusion models, proposes. Exactly as we just said, they sample a sequence from their data set, they sample a time t, in this case uniformly, they do the forward noising process with the Q that we had defined, they calculate the loss function caring only about what the model outputted for the masked tokens, looking at the probabilities assigned to the ground truth tokens, calculate the gradient, run the optimizer, and blah, 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 repeat this in your training loop. One thing that I do want to mention, and that also this paper Block Diffusions mentions, is that a particular challenge with these models is that you might be working with a loss function that has a lot more variance during the optimization process, because you're basically asking the model to solve quite a complicated task. Like you're showing it sequences with very arbitrary maskings that is different in every iteration that you do. So there could be a lot of variation across your iterations. And in this case, that's exactly what they show and what they also mention as a training challenge. The red brownish line is the diffusion and the blue one is the autoregressive. And you really see a much nicer training curve of the negative log likelihood for the autoregressive model than for the diffusion, which kind of like bounces around quite a lot. So be aware of that. Once you've trained the model, how does the inference actually work? And I'll spend a little bit more time going over this, but first let me give you the general idea. So at inference, similar to how you would start with completely random pixels and denoise into an image, we here start with a sequence that is completely masked, and in steps we would like to denoise this into a sequence that actually makes sense. So what do? We take our masked sequence of masked tokens, we pass this through a model, and we get out for every masked token the particular probability distribution that the model assigns to that particular token. Now, the critical part here is that we will not directly accept all tokens, but we will sort of gradually accept more and more and more. So in the first iteration, we might accept some tokens, and I'll talk more about how we make the decision of which tokens we actually accept. We fix these to their unmasked probabilities in some way by sampling or by greedily taking the most likely token. We take this now partly denoised token, pass it again through the architecture that we had, get again the probabilities, again fix certain tokens, take that sequence, pass it again, and again fix certain tokens until we are ending up with a full sequence. So where does this promise of speed come from exactly? So the benefit that this diffusion approach gives us is that we are not limited by this left to right, one by one token generation. In diffusion models, we could actually denoise multiple tokens at once. So in this image, we could actually accept a few tokens in one go. And this would definitely save us iterations because we would have to have less forward iterations before we get to our full sequence. And the reason that we can actually do this is this kind of like implicit conditional independence assumption that we take, which is that whenever we predict these probabilities for the masked tokens, we're kind of demasking all of them independently. So we are predicting maybe x3, the third token, at the same time as x6, but x6 doesn't know what x3 was, and x3 doesn't know what x6 will become. So there's this kind of like independence between tokens assumption, and this is the thing that could potentially be nice, because we could generate multiple tokens in any order in one go. But as I'll show you in a bit, it's also potentially challenging. So the other nice thing is that, frankly, this approach is kind of really a generalization of autoregression, because if I fix my masking schedule to go from left to right, and if I fix my denoising, accepting the token framework to only accept tokens kind of one by one, again from left to right, then I'm basically back at autoregression. So there is this paper, You're Absorbing Discrete Diffusion Secretly Models the Conditional Distributions of Clean Data. And they have a nice derivation where they kind of formalize this idea where they say masking tokens randomly and predicting them is really approximately equal to training over all possible generation orders. So again, we're not limited to just autoregressive one by one left to right, but we're actually doing all kinds of possible generation orders that you might like. This is why it's harder to train, maybe more complicated because we have to cover more generation orders, but it's also what potentially would give us more freedom to make these models work in a good way. So the thing I want to highlight is that inference schedules actually do really matter. So this choice of how do we actually denoise, which tokens do we accept and which ones do we remask and pass again in the forward pass through our model, it really critically can change the quality of the generated tokens. So let me show you a few schemes that people are using right now, but potentially this is also really an area of more improvements. So one very obvious approach is to just say, okay, I'm just going to randomly accept the tokens that I like. So starting with my masked sequence for a certain number of steps, where this number of steps depends on how many tokens k I accept in one go. I'm going to, for example, sample tokens either greedily, or greedily meaning I just take the ones that are most likely, or stochastically where I sample from, again, a categorical over the vocabulary. I keep the tokens that are already unmasked as is. So once unmasked, you always stay unmasked. But out of the ones that were still masked, I'm just accepting a random number k of tokens completely randomly. This approach of completely randomly can be changed by doing something a little bit more clever. So you might say, okay, I'm not accepting k random tokens, but I'm accepting the k highest confidence tokens. So for which there is a probability to one of the tokens in the vocabulary that is very high. Or alternatively, you could say, okay, I'm accepting the k lowest entropy tokens. So kind of like the certainty of my distribution is very sharp. A generalization of this is that you might not say I'm just accepting the k highest ones or lowest entropy ones, but you could fix a threshold and you could say, okay, in every iteration, I'm accepting that number of tokens for which the confidence is above this threshold or the entropy would be below the threshold. And maybe you say, okay, if none are above or below it, then I actually accept the highest or again lowest, depending on if your confidence or entropy single token. The other good thing to show about these diffusion models is that, as I said already at the start, the performance really does begin to match autoregressive models. So this is again from the Inception Mercury model. And they kind of show that if you position speed against performance or accuracy, their model is kind of like, in their words, the most attractive quadrant, aka it seems to be really fast, but it still matches the performance of other autoregressive models that might actually be bigger or slower. Same thing from the Lada paper. When they trained their diffusion model of 8 billion parameters, and if they then compare to comparable size autoregressive ones like Llama, Qwen, Mistral, DeepSeek, they at least get that on certain evaluations, the diffusion one is not too far off from the autoregressive one. On other ones, you can actually see the numbers, but it's still not as good. But okay, maybe diffusion models are kind of getting there. At the same time, I would highlight that things are not as trivial. So as I was making this video, I was kind of going through the more recent literature as well. And there's this one paper, Lada 2.0, which is a follow-up on the original Lada paper. And I guess the original Lada paper sort of made the claim that if only we scale up these diffusion models, we can match the performance of these autoregressive ones. And they kind of write, okay, current research was actively focused on challenges such as specialized training regimes, efficient sampling strategies, efficient inference, and so forth. But that meant that models operate at a smaller scale. And so in this Lada 2.0, they really wanted to take this diffusion approach and scale it up to a much bigger size. However, what they eventually ended up doing is that they did end up using the autoregressive foundation model as a kind of starting point. So they just they took this pre-trained model that was autoregressively pre-trained and continued training that by turning it into a diffusion model. So the good side is, as their graph shows, they were able to get performance that was comparable to Qwen 330b. But at the same time, they kind of did start with an autoregressive approach as well. Another paper, which kind of goes against the things that I was saying before. So before I was saying, maybe this arbitrary demasking order generation is a nice thing. This paper, Parallel Bench, actually says that maybe this is also a limitation. Because as I already told you, the reason that we can unmask, we can be faster than autoregressive models is that we might be able to unmask more tokens in one go. But this means that token 1 gets unmasked without knowing what token 2 is going to be, and token 2 gets generated without knowing what token 1 was. And here they show that, in this example, pick a random city for travel, New York, New Orleans, Mexico City, or Panama City. Because the model doesn't know what the next thing is generating or what the preceding thing has generated, it ends up saying, new city, which is not an answer that makes any kind of sense. So as they say, without knowing what was generated for the other tokens, we really might end up with completely wrong generations. And then there is a LADA 2.1 paper that also notes that this is a limitation, and they sort of allow for a more complex generation process. So instead of simply saying what we said before, which was once a token is unmasked in the demasking, denoising process, it forever stays unmasked. They also actually allow for token editing or correction, where they say, okay, we keep the token as is if the argmax confidence, the new argmax confidence in the current forward pass through the model is low, but we actually replace it if the new argmax is different and the confidence is sufficiently high. So we demasked tokens actually get another opportunity to be demasked or replaced again. And another recent paper known as Introspective Diffusion Language Models, they did another thing where they noted that they started the paper by saying, let's actually look at the things that make autoregressive models great, and let's try to leverage some of those intuitions for diffusion models. And one of the things that they ended up doing is they ended up going back to applying strict causal masking whenever we train the model. So they removed this whole non-causality approach. And with all of this, I basically want to say that if you look at where the diffusion models are sort of moving, at least in the papers that I could find, is that they either start with pre-trained autoregressive models, so leveraging all the hard work that was done by the autoregressive approach, or they actually change the training objective or the generation objective in all kinds of hacky ways in order to just make it better, or they remove this non-causality, so this potential benefit of arbitrary order gets removed, and it brings us again closer to autoregressive models. So all in all, a little summary, diffusions were cool because they removed this left to right one-by-one generation limits. This promised speed and solving potentially more interesting tasks. But so far, I think the diffusions still sort of lag behind. And attempts to scale them in the literature show that they leverage pre-trained autoregressive models. They do all kinds of tricky things with token editing and actually sometimes even introduce back causal attentions. So I guess the verdict is still out on which model will be the best, or whether all of these approaches may kind of converge into something that mixes diffusions and attentions, diffusions and autoregressive approaches into a single unified viewpoint.